All right, I think we're set. So Shenhong is currently a PhD student in the physics department at National Taiwan University. His research interests lie in algorithms related to Hamiltonian simulation. He will present his work on utilizing the randomization techniques to improve the accuracy of the product formulas. Let us all welcome our speaker. I think you're muted.
Hi, can you hear me? Oh yeah, good. Okay. Hi. My name is Chen Hong, and today it's my honor to present you my work, doubling the error order of approximation via randomized product formula, and which is the joint work with Dominic Barry and Min Xie. And I will split my presentation in 3 parts. And first, I will talk about a little bit about the motivation, like what the importance of the quantum simulation and why we need to care about the Hamiltonian simulation. And next, I'll move on to introduce several well-known Hamiltonian simulation algorithms, for example, like product formula and Taylor series expansion. And the third one is the quantum signal processing. And that's part. I'll focus on the one of the method that is the product formula, and I'll use the randomized technique to improve the accuracy of the product formula. And that's the outline of my talk. Oh. Yeah, I haven't shared the slide. Okay, is it? I'm not listening very well. Oh, so you mean here? Okay, fine. Okay. So, yeah, there are several applications of quantum computer. Like first, the well-known application of quantum computer is that we could use quantum computer to break RSA algorithm, which is the well-known Shor's algorithm. And the second one is we can use this technique to solve the optimization problem. And there are several algorithms has been proposed, like QAOA or quantum annealing. Or recently, there are several novel algorithms have been proposed based on the lim-dot equation. And the third one is we can use quantum computer to simulate quantum systems and their dynamics. So today, my talk will focus on, it will related to the third one, like we could use quantum computer to simulate the quantum dynamics. And this is a very crucial, important application for quantum computer. And I quote a sentence from Richard Feynman. He said that nature is not classical, and you want to make a simulation of nature, you had better make it quantum mechanical. So which means that quantum computer is the best platform for us to simulate and to study the behavior of the quantum system. So, but the problem is that our current quantum devices is not good enough. So how can we efficiently and accurately construct the evolution operator with elementary gates is a pivotal issue. Like we could consider, because like our case is too complicated. So sometimes we need a lot of qubit, or we need numerous elementary. So if we can design an algorithm, we can efficiently and accurately simulate the system with few resources, then they could be useful for the quantum simulation area. Oops. Okay, so basically, like the quantum simulation is the area they are trying to focus on, study the dynamic of the system. And given the system Hamiltonian is the big H, the dynamic of the system is given as it's determined by Schrödinger equation. Like we start from the state psi 0, and we can have the state at at time t by implement the time evolution operator on it. So in my talk, I'll focus on the time independent Hamiltonian. So in this case, we would like to construct a quantum circuit U to approximate the exact unitary operator exponential minus IHT. So we aim to construct this approximate unitary U and to use fewer quantum resources like quantum elementary gates or the qubit resources. Oops. Okay, but before that, we need to obtain the effective Hamiltonian of the system. So here I take quantum chemistry as an example, like how to obtain the Hamiltonian of the system. And then once we obtain the Hamiltonian, then we can use it to study the dynamics of the system. So there are several ways to obtain the Hamiltonian. And in quantum chemistry, there are major three steps. Like first, because in quantum chemistry, there are interaction between electron and nucleon. And so for step one, we can use the Born-Oppenheimer approximation. That is, when the mass of the nuclear is way heavier than electron, then we can use this approximation to reduce the interaction between electron and nucleon. So it could give rise to these terms. Like there are three terms. Like first one is the kinetic terms of the electron, and the second one is the interaction between electron and nuclear, and third one is the interaction between electron. So once we have this approximation, then we can transform it into second quantized form. And the second quantized form would have some raising and lowering operator. And when we use the second quantization, we need to choose a fixed basis. And this basis can help us to compute the coefficient HPQ and HPQRS. So when we have this second quantization form, then we can use several methods to encode it onto qubit. Like here, I provide you a quite common transformation, that is Jordan-Wigner transformation. And in this transformation, they store the occupation number of the spin orbital into the 0 or 1 state of the qubit. So here, on the left-hand side, the state Fm-1 to F0 represent the state of the occupation state of the electron system, and we can directly map to the qubit system, which we use the M qubit, and each qubit represent the occupation status of the orbital. So like if the Q0 is 1, means that the orbital 0 has 1 electron on it. And then we could also transform our raising and lowering operator through a series of Pauli strings. So like for the AP operator, we can implement a sequence of P Pauli operator and acting QP operator on it. And Q is defined as Pauli X plus I Pauli Y divided by 2. So in this transformation, that we can transform our second quantization Hamiltonian into the form that we can implement it on quantum computers. So as it turned out that when we consider the practical cases, that is, we consider some complex molecule, the size of the Hamiltonian will be very, very large. For example, here I list 3 different chemical compounds. One is ethane, and second is carbon dioxide. The third one is propane. And as you can see here, if we map the Hamiltonian of the molecule into several summation term, the L is a summation term. As you can see, for example, like in ethane, the L will be around 241,000 turns here, and it requires 46 qubits. And for carbon dioxide, it requires 113,000 turns in Hamiltonian, and it requires 55 qubits. And if we consider more complex molecule, and the scale of the L will increase very much. So it means that in the future, if we want to study the more complex molecule system, the Hamiltonian terms will be more complex. So at that moment, we need to the importance of constructing an efficient and accurate Hamiltonian simulation algorithm would be very important. So here comes the issue that how can we effectively and accurately simulate Hamiltonian with lesser resources? So the Hamiltonian simulation problem is that given a Hamiltonian and evolution operator V, and we aim to construct a unitary operator to approximate it in epsilon close. And if we evolve the system from t equal to 0 to t equal to t, and we can split it into sufficient large R steps. And if the R is large enough, we can approximate the average operator with under certain error rates. And if yeah.
So you're worried about the simulation.
Yep.
And you want to make
quantum chemistry is my motivation, like because the system is too complicated, and I'm thinking, how can I design the algorithm that can use fewer resources like quantum elementary gates and can achieve the same amount of error rate?
The problem that you have is that if you want to actually describe the Hamiltonian and write the Hamiltonian for these molecules, they are going to, even though you can have some approximations depending on mass and everything, it's just too many terms.
Yeah.
So if you try to put this on a computer, this is going to get crazy.
Yeah, and also if the simulation time is very long and very large, and the number of elementary gates that you use will increase as well.
Is this quantum simulation, or you're talking about classical simulation of the molecules?
No, here I mean that we use quantum computer to simulate the dynamics of the quantum system. Like we do the experiments on quantum computer.
So in this case, even in the case that you actually have a quantum computer simulate the molecules, it is still going to be very costly.
Yeah, like for now, we are in next area. Our computer is not that powerful because we have some error rates and we have limited coherent time. So we cannot have an unlimited quantum resources later to use. So under this constraint, we can use, if we can construct or design an algorithm that can use the fewer qubit or lesser quantum circuit, then we can achieve the same text, then that would be beneficial.
So the point is that perhaps a quantum computer will be able to simulate this efficiently.
Yeah.
But we are not there yet. So
Yeah.
That might come.
Yeah.
We need to be careful with the resources.
Yeah, because it has been shown that the quantum system on quantum computer is in the BQP class, which is BQP complexity class, which means that it's efficient for quantum computers. But for now, because our quantum device has some error, so that's the reason why we need to study this.
Okay. So here, when you divide into R steps,
yeah.
So you only need the epsilon error at the end of every step.
Yeah.
So in between steps, the error could actually be larger. That's fine. Yeah, you want to look at.
But sorry, could you state your question again?
I mean, it's just that, like, I mean, of course, when you run this, of course, it runs continuously.
Yeah.
So when you're using like an approximation,
yeah,
then the approximation could be bad at certain times, Right.
Yeah.
But maybe at the end of the day, you only care that at the end.
Yeah. Because
it could have momentarily had large errors at certain times, but this is not about it.
yeah, because we only care the target state, that is the state at time t. If it's distance between our target state and our experiment state is close enough, and that would be meaningful. So, okay.
I think the error of if you don't control the error,
That's true. I even
Yeah, so that's the reason why. So in each step, we also need to ensure that in each step the error is lesser than certain amount of error. Okay, so here if epsilon is at the order of t over r to the power of k, then we say that this Hamiltonian simulation scheme is of error order big K. So here I list several well-known Hamiltonian simulation algorithms. First three terms, which is related to product formula, and first one is the first order product formula, and second one is the two-case order product formula. And the last two terms, they use a different technique. The truncated Taylor series, it used they use the Taylor series expansion to expand the evolution operator, and they truncate it as certain order, and then they use some linear combination of unitary to add those unitary, and then they use the amplitude amplification to get the state that we are interested. And then the third one is about the quantum signal processing. That is, they use some quantum walk scheme and plus some quantum optimal control scheme to help them achieve the gate complexity in linear time. So then I'll spend a few slides to talk about the Taylor series method and quantum signal processing. And after that, I'll move on to our topic today, which is related to the product formula. Yeah. So here, as you can see here, the truncated Taylor series means that we simulate the Hamiltonian dynamic with the Taylor series. So first, there are three steps. First, our evolution operator is exponential minus IHT over R, and we can expand it into a summation of several terms, and we can truncate it as certain order. And if we can express the Hamiltonian into a linear combination of several unitary, then we can write this truncated term into several linear combination of unitary. Then we can do the linear combination of unitary on a quantum computer to sum all these unitary. And then, but it turned out that when we use the LCU algorithm, actually we can get the state that we are interested in with certain success probability. At that moment, we need to use some previous amplitude amplification to increase the success rate of the probability that we are interested in. So it means that the whole scenario would be that it is our evolution operator, and we expand it and we truncate it as a certain order, and we if we can express the Hamiltonian into certain unitary, then we can use LCU to implement it, and we use amplitude amplification to amplify the success rate of the state that we're interested in. So that's the main scheme of the truncated Taylor series. And the other one is the quantum signal processing. And there are three main steps for this quantum signal processing. Like first step, we need to block encoding the Hamiltonian. And here, we also assume that the Hamiltonian can be written as the summation of the linear combination of unitary. And its eigenstate is EK. And first, we plug encoding Hamiltonian into the joint Hilbert space of the ancillary space and H. We denote ancillary space as HA, and the target state lies in the Hilbert space HS. So then we need to construct the state GA. The A here denote this state lies in the ancillary space, and we need to construct this GA, which encodes the information about the coefficient of this HA, because here HA is a combination of sum over alpha j uj, and we implement it onto we can do that on a corner circuit, and we encode it, and we can prepare the GA state, and then we need to prepare we need to use the operator M, which is the control operation, like at certain ancillary state, we implement the uj, and then as it turned out that under this scenario, we can block encode the Hamiltonian into the M operator. So that the block encoding means that the M, there's a H over alpha actually lies in the certain block of the operator M. So then the second step will be similar to the group research. We can define the operation. The first one is the M operation. The second term is the reflection operator. And when we use this operation, we can have the eigenvalue exponential I arc cosine ek over epsilon over alpha, and we can we can visually understand it as a like first as just like the Gruber algorithm. First, we prepare the state in GAEK state, and when we implement the M, it will reflect the state to this one, and then we reflect our state to the rotate it to the other side. So just like the Gruber algorithm, but actually all we care about is the eigenvalue state, because you can see that if we can use some kind of transformation to transform the eigenvalue from exponential I arc cosine ek over alpha to exponential minus I ekt, then we can implement the Hamiltonian simulation. So then the next step would be like, how can we achieve this kind of transformation? They use the quantum signal processing technique, and the high level picture of the quantum signal processing is that they use the control rotation from the single qubit to approximate the exponential minus IT alpha cosine. So for example, here R phi is a rotation on the single qubit, and we can implement it sequentially, and each rotation is with a parameter phi, and we can implement it uncontrolled rotation. And as it turned out that because this is a 2x2 matrix, and we can express it in this term. This is A identity, IBZ, IC Pauli X, and ID Pauli Y. So then when we can use this, and we can implement on the control operation, and we can approximate this transformation. The transformation that we need to achieve is this, like we need to transform the exponential I theta to exponential minus IT alpha cosine theta. If we can do that, then we can transform the eigenvalue from exponential I arc cosine ek over alpha to the eigenvalue that we want. So in quantum signal processing, they need to compute the phi angle phi 1 to phi m, such that the distance between absolute value of A plus IC minus exponential IT alpha cosine will be less than epsilon. So the idea here is that they use the single qubit rotation and they want to transform eigenvalue from exponential I theta to exponential I t alpha sine theta. So if we can achieve that, then we can transform the eigenvalue of the quantum walk that we defined in previous step from this term to exponential minus I ekt. Yeah, but there's still a lot of details here, and if you are interested in it, you can check the paper from 2019. Yeah. So although like there are several algorithms they can, for example, like quantum signal processing, that it can achieve the gate complexity in linear time, but product formula are still very competitive. And here I provide 3 reasons. The first one is that formula does not require any ancillary qubit and make it suitable for near-term devices, because near-term devices we have limited qubit, and if the algorithm can save us a lot of ancillary qubit, then that would be very good. And the second one is that in some cases, a product formula perform well when incorporating the information of the commutative structure of Hamiltonian. And the third one is that although other algorithms had a logarithmic dependence on the allowed error echelon, but in practical, when we do the simulation, we will always fix the error rate to some certain value. So the algorithm only provides polynomial reduction with time in gate complexity. So based on this reason, the product formula are still very competitive. So yep. No, here I mean that although other algorithms they can improve the error rate in logarithmic, but when we do the quantum simulation, we will not always require the error rate lesser and smaller and smaller. We will require the error rate to be specific value. And when we do that, and when we do the simulation time, at the moment, the improvement will be polynomial reduction with time t. Yeah, I mean, like for example, in chemistry accuracy, they require, I remember, it's a 10 to the power of -6. So in that case, the most important things would be how can we save a lot of resources when we increase the simulation time. Yeah.
But at the moment, the product formula and the signal processing will have the same dependence.
Yeah, one is linear in time, one is the is a t over 1 plus 1 over 2k, but quantum signal processing, it requires a lot of ancillary qubits. Yeah, so so when we do the quantum simulation to consider different aspects, like how many qubits that we use, how many elementary gates that we can use, so that we can find the best algorithm that we can use. So here I just want to argue that product formula are still very competitive, and it's still worthy to study the behavior of product formula in different quantum systems. Oops. So here I provide the data, which is from Andrew Trice in 2018. Their target system is the unsigned Heisenberg model, and with the periodic boundary condition. And in this figure, the blue dot is the truncated Taylor series that we just mentioned before, and green dot is the quantum signal processing, and red dot is the product formula. And when we increase the system size, as we can see here, the product formula always has the requires the qubit number which is lesser than truncated Taylor series and quantum signal processing. So, which shows that product formula actually can save us a lot of qubit usage. So here, I'll move on to our third part, that is our results. And when we consider the two-case order random shorter formula, this random shorter formula is a randomized technique introduced by Andrew Charles, and which I'll introduce you later. And our method can double the error order from 2k plus 1 order to 4k plus 2 order, which means that with almost the same amount of corner circuit, we can double the error order from 2k plus 1, which means that we can increase the accuracy of the product by using the randomized technique. And when L is at the order of little r t over epsilon to the power of 1 over 1 plus 1 over 2k, at this order, our method is advantage over the existing higher order product-based formula. So here I list the table. And the first one, random shorter, which is proposed by Andrew Charles, and their gauge complexity is the maximum over these two terms. And our method can is better than their method when their second term is dominant, which means that when their second term dominates, means that L is an order of little o t over epsilon to the power 1 over 1 plus 1 over 2k. So at this moment, our algorithm can perform better than their randomized product formula. This is our result. Oh, L means the number of summation term in Hamiltonian. Summation term. Yeah, I can show you quickly. Like,
Oh, I see. How many?
Yeah, like this. Yeah, actually you can express it the several summation term, and L is the number of term in Hamiltonian.
And H is the.
Actually, it could be some local, like for K local Hamiltonian. And so, for example, like in Heisenberg model, HI would be this xj tensor product xj plus 1, like this term. No, this in this case is a two local, but in general case it could be K local or it could be the general case. Yeah, so this term would be one of the summation term in Hamiltonian. So we consider that if L is the order of the little r t over epsilon at this term, then our method is advantage over the existing higher order product-based. So here I quickly introduce.
Why do you call it the gate?
Here, actually, here I mean that the complexity of the exponential, like, because as later I'll show you that actually in product formula we need to implement a sequence of exponent unitary operator, and then in gauge complexity we need to evaluate order of the number of the exponentials that we use in the product formula. Yeah, and that exponential can be decomposed into some elementary gates. Yeah, so here I mean that actually the elementary gate, it depends on which devices that you use. So here we evaluate the scale of the exponential term.
When you say that it depends on the device that you use,
because like if different devices that use different sets of universal gates. So like if you want to decompose certain unitary operator,
there's going to be like an optimal set base.
I guess, but here we didn't consider like certain type of gate set. We care about the certain exponential that we use, and if you consider the certain gate set, it will add the polynomial overhead. So here, per formula, it means that we want to construct the UT over R. We can approximate V in epsilon codes. So here, what I mean, the exponential means here, like we consider the first order formula, then we can split the Hamiltonian into several unitary operator. So what I mean exponential is means that each blue blocks represent a exponential terms. Then in our gate complexity, we means that we evaluate the scale of the how many blue blocks that we need to use in this formula. So like for example, in this first order formula, its gate complexity is that big O of t over square, t square L cube over epsilon. And if we consider the further decomposition, and you will need and mod the constant factor for the number of. So here we have the first order Taylor formula. Actually, we also can have the two case order Suzuki formula. And here I show you the explicit form of this formula, and we can recursively construct the two case order formula in this way. And that is first we introduce when we construct the two case order formula, then we can iterate the generate the two case order Suzuki formula. And its gate complexity is at the order of big O of t over 1 plus 1 over 2k. And yeah, and compared to the quantum signal processing is linear in time, but in higher order product formula is not linear in time. But when k is larger enough, then the gate complexity will almost linear in time. So here we could introduce the randomized technique into product formula. And when we introduce this technique, it turned out that it can help us to improve the accuracy of the product formula. So like instead of the fixed total unitary operator S2K, we can sample a unitary from a given set UI according to the probability, well-designed probability PI. That the content channel constructed by this UI and PI can approximate the V. V is the content channel constructed by the averaging operator. And if we can design a good PI and UI, and it can approximate the V channel in epsilon codes. So here, 17, Earl Campbell, he proposed the mixing lemma. He states that how we can bound the distance between the mixing channel, that is epsilon, and the target channel, that is the state that we're interested in. And it depends on two factors. One is the distance between each unitary operator and the target averaging operator. And the second is the average of the sample unitary operator and the target unitary operator. So it means that when we can evaluate the distance between each unitary operator and averaging operator, also the average of the unitary operator and the averaging operator, then we can bound the distance between epsilon and V. So actually, my work is based on this mixing lemma, and to find a good set of unitary UJ and PJ to see how we can improve the accuracy of the product formula.
When you say mixing of the unitary,
yep,
it is implemented with probability, so it means the distance is only set by probability or
what do you mean probability?
How do you sum the unitary?
Oh yeah, that's good. So we implement the unitary, like we sample the uj based on the probability pj, and in each step we implement the unitary based on the sample that we pick. So, and this bound say that if we can design such a PJ and UJ, then we can approximate BJ by using this mixing lemma.
So it means that this is only set by with expectation.
Yeah.
So what is the norm?
Diamond norm. Oh, it's a spectral norm. Yeah, algorithm. So here, this is the randomized Schroeder formula that I mentioned, which is the work from Andrew Trust in 2019. And here I give you a simple example that how to randomize the product formula. Like if we consider Hamiltonian as the sum of H1 plus H2, and we consider the first order approximation H1, H2 in this form, then we expand it. You can see that the error terms at the second order come from because when we do the expansion, this term should be H1, H2, and H2, H1. But and we can reverse the order of the Hamiltonian, then we can also the reverse order term here. So then their idea is to mixing these two unitary, and by using mixing lemma, they can improve the product formula to the third order. Yeah. So it means that actually you can just average these two first order approximation, and you can see that it just recover the original unitary operator to the second order, and they consider using the mixing lemma, which means that they use they sample each unitary with the probability 1/2 here. Then they show that the diamond norm between this quantum channel can be bound by T/R to the power of 3. Yep.
So it means you when you implement the sample and
Like when we in each step we can pick each this either H1 H2 or SH2 H1 with the probability 1/2. Yeah, and in each step we can do the same. We can repeat the same procedure times. Yeah.
So it means that you require the steps must be large enough to take this solution to be satisfied with high probability.
Yeah.
So you need some probability concentration.
Yeah. So in Qifang's paper, they also analyzed several topics about concentration issue.
About the steps.
About the how many samples or how many samples that you use to concentrate to the.
I think I'm a little bit confused. I remember lately that the Schroeder formulas are used in the delta community.
Yeah.
So if you have an explanation of 2 or more Hamiltonians, then you can kind of make an expansion, kind of truncate the series, and make an approximation for what would be the action to be divided in different explanations, right? So I would imagine that these things are only done when you have systems with non-commutative Hamiltonians.
Yeah.
The first thing.
Yeah, the first thing. If it's commute, then that's good. We don't.
Yeah, I imagine it would be much easier. The second thing is that I see that when you do this, the composition of the S1 into H1, H2, and H2, H1, you're already using 2 exponential terms. So where is the Schroeder formula actually being used? Because you're just making, here, or I mean, I should say them, right? They're just making the expansion for the exponential, normal one, and the other explanation, and just like making the product of them, right? So where is the Trotter formula here?
Oh yeah, actually here I use the first order product formula here.
Okay.
So we can do the same thing on the two-case order product formula. Like we can, in two-case order product formula, we can also consider the permutation of all Hamiltonian in product formula. Then they show that it can slightly improve the accuracy of the product formula.
Like improve the accuracy.
I mean that slightly means that later I'll show you that their gate complexity will also constrained by the average of the unitary, the distance between the average of the unitary and the target average operator. So here they show is the actual bound, because in mixing lemma I mentioned that if we want to bound the two channel, we need to first evaluate the distance between each sample unitary and the target evolution operator. And the second one is the average of the sample unitary operator and the target evolution operator. And as it turned out that their gate complexity will limited by the second term, which is the average of the unitary distance. It's also at the order of 2k plus 1. Yeah. So actually, yeah, you're right. We can treat the same randomized technique onto the Trotter formula, and it can improve its accuracy here. And so here, so then my work is to design a better ensemble PI and UI such that it can have a better performance and gate complexity. Yeah. So then, because in Andrew Charles' work, the distance between each evolution operator and a sample unitary is at the order of 2k plus 1, and my work is to design a better ensemble PI and UI such that the distance of each unitary operator and the target evolution operator is at the order of 4k plus 2. If we can achieve that, then we can, according to the mixing lemma, then we can double the error order of the product formula. Because from the mixing lemma, we can the diamond distance between the evolution operator, the quantum channel, and the epsilon, which is the quantum channel constructed by our PI and the UI, can be bounded by the distance a squared plus 2b. So if we can find a well-designed P probability and a sample unitary such that B is at the order of 4k plus 2, then we can double the error. Yeah, because like in Andrew Charles' work, this term is not 4k plus 2, and we want to improve this term to improve that make it to at a similar order to the first term. Then we can double the error order. Yeah. So here's our goal that we need to design the unitary U and P such that the distance between target unitary and the average of U is at 4k plus 2. So there's a recipe, and there's 3 major steps. Like first one, for any product formula, we can define the D operator, which is V minus S2k. S2k is the 2k order Trotter formula. Then our recipe is that first we need to know the explicit form of the V dagger D plus dV dagger, and we can show that actually the even order term will be 0 only, and the remaining term will be the odd number order. That is the 2k plus 1, 2k plus 3 to 4k plus 1. And then we can design the corresponding unitary U and P such that the average of the unitary can satisfy our 4K plus 2 requirement. Yeah. So quickly go through our step. So first is that we consider a kind of sandwich structure. That is, we consider the 2-case order Schroeder formula, and when we consider insert this kind of operator 1 minus v dagger d minus dv dagger, and actually this term can approximate the evolution operator up to 4K plus 2 order. You can show it with some matrix analysis. And then our goal is to design a set of unitary, and its average can approximate the middle term up to 4K plus 2 order. Then so we need to check what the explicit form of this v dagger d plus dv dagger, and we show that the following statements are true. Like the even order terms up to 4K order are cancelled. It means that we only need to consider the order gamma equals to 2K plus 1, 2K plus 3, up to 4K plus 1. And also, we can group term as the order in gamma such that the elements in HJI are all Hermitian. So which means that if we can satisfy these two conditions, then we can design using a unitary, insert a unitary between this S2K and between this S2K such that we can recover the terms up to 4K plus 1. So it means that because in the previous I mentioned that we consider sandwich structure, and we need to consider using the unitary to recover the operator that is 90 minus v dagger d minus dv dagger. So we use the unitary operator to recover that, and that will leave several error, which is at the order of 4K plus 2. So then, because gamma is the odd order, so it means that actually the imaginary term comes from this lambda to the power of L. And we also show that the elements in HJI are all Hermitian, which means that this H actually is a Hermitian term. So it means that we can design a unitary such that the zero order term and the first order term can recover the terms in the red highlight in red. Here. Okay. So here I'll quickly go through the two claims that I just mentioned before. First one is that actually the even order term up to 4K cancel. So it means that we only need to consider gamma equals to 2K plus 1, 2K plus 3, up to 4K plus 1. So we can show this by using the result from Yoshida 1990s. And you say that actually we use the two facts. One is actually the terms in between can approximate this S2K dagger, VV S2K dagger up to 4K with the 4K plus 2 error order. And because this S2K dagger, VV S2 dagger is satisfy the time reversibility, so the error order lower than 4K plus 2 is all odd. So it means that in this term, the even order is canceled out, only left the error order term. So which means that this term would be the same situation. That is, gamma would be the odd order terms here. Yeah. Gamma is the order that I need to use the unitary to recover it.
When you say terms are going to cancel.
Yeah.
It means that the symbol that you're trying to find to be like optimal for your goals needs to have even terms that cancel. That is,
Sorry, what again?
like you said that you're trying to bound the error, right?
Yeah.
And to bound the error, you need to find an ensemble that fits well.
Yeah.
With the diamond.
In this case, because we use the mixing lemma, so we care the operator norm between V and the average of.
Exactly. Yeah. So you need to test the properties of this ensemble.
Yeah, yeah.
It is the case that one of the properties that you need is that this even elements are going to cancel.
Yeah. 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 So and the second claim is that because the symmetric form of the S2K and V dagger, then we can group the terms in V dagger D plus DV dagger to be Hermitian. So that would be great. Means that we can use a unitary to recover the terms in between. So actually, then we can design the quantum channel with ensemble P, PHL and the UHL theta. So here's some remarks. Actually, our method can also fit to any 2-case order symmetric product formula. There's Suzuki formula is not the only formula that can achieve 2-case approximation. Also several different product formula, and our method can also extend it to other that kind of product formula. And also the second one is that actually implement this unitary is difficult, but when we consider the case of quantum chemistry, like the Hamiltonian expressed as a linear combination of the Pauli string, then because we can easily calculate the product of the different Pauli string, then we can prepare this unitary UHL tilde is in quantum chemistry case. Yeah. So here I gave you a simple example, like how to construct our randomized formula. So given H equals to H1 plus H2, and we want to construct the randomized formula based on this second order Schroeder-Suzuki formula. So like I just mentioned before, we need to know the explicit form of the V dagger D and minus DV dagger. So we need to do some expansion to know the information of this term. And as I mentioned before, that because the even terms are canceled out, and we only need to care about the odd order terms. So here we need to know the explicit form of this lambda square and lambda to the power of 5. And then when we know the explicit form, then we can group them to recover it to the unitary here. So here, like for example, here U03 means that the first term at the third order, then we can see here H1, H2, H1 actually is the Hermitian term. And there's an imaginary term contained in it. So it means that we can, actually this is a unitary operator. So similarly, for the fifth order term, we can combine these two terms as a Hermitian term. And there's an imaginary number in this coefficient. So we can use unitary operator to realize it. So then this simple example shows that how we can use our randomized technique to improve the error order. So then the third step would be like, then I'll need to sample the unitary correspond to the probability. That is the unitary in the structure of secondary structure. Like
we insert the correction unitary between the second order Schroeder formula and with a well-designed probability that we propose in our paper. So that in this case, then we can approximate the target evolution process up to fifth order in lambda. So here, the last part, I'll provide a numerical analysis. Like we consider the n-side Heisenberg model, and we consider two scenarios. One is like we fix the evolution time t, and we change the system size from n equal to 10 to 100. And the scenario 2 would be like we fix the system size equal to 10, we change the time from 0.1 to 10 to the power of 6. And this is our result here. And the left-hand side is the figure shows how our randomized technique works when we increase the system size from 10 to 100. And the blue one is the deterministic Schroeder-Suzuki, and the red one, red dots and red triangle means it is the randomized technique which is proposed by Andrew Schwartz. And the green circle and the green triangle means the randomized technique proposed by our work. And this shows that when we increase the system size, our we need lesser number of exponential. And also when we consider fix the system size and increase the evolution time t, our method also need lesser number of exponential. So here I give the summary and outlook. Like we proposed a new randomized scheme for symmetric two-case order product formula, and that can double the error of the formula. And also, the gate complexity of our scheme is better than current deterministic two-case order formula, and can better than the existing higher order randomized product formula when L is an order of little o t over epsilon to the power of 1 plus 1 over 2k. So, and then the outlook would be like whether we can combine our randomized technique to other Hamiltonian technique. And such as the linear combination of unitary, quantitative proceeding, and that would be the open question. And thanks for your attention.
Okay. Yeah. Thank you very much for your presentation. Do we have any questions from the audience? Can you? Do we have more questions? Okay, if that's not the case, let me thank you again for the presentation, and let me stop the recording.